So welcome to lesson number 6 from Light and Sound, where we're going to continue talking about interference and diffraction. Now we're on to the last part of this, which is part 4. It's all about the spectrometer. This is a very, very short lesson. You need to understand the spectrometer in order to be able to do experiment L5, which we will be doing later with the leaving cert question. So scroll down through your notes and get to that final part of this particular lesson. So we're on 5.4, the spectrometer. So you need to be able to draw a diagram of the spectrometer. First of all, what is the spectrometer for? Well, you can look at all kinds of spectra or rainbows through a spectrometer. But basically, what will we use it for in the leaving cert? Well, it's going to measure the angles at which bright images are formed from a diffraction grating. You know the way the light passes through a diffraction grating and you get all the different orders of bright images? Well, this can measure the angles at which they're formed. Now, I need to be able to draw a diagram of it, and it's a very simple diagram. So here's my diagram here. I've got a circle. That will represent the turntable right in the middle of the spectrometer. And on that turntable, you are going to place a diffraction grating. That diffraction grating, as you know, has lots of little gaps, hundreds, thousands of gaps per millimeter. You don't have to put the gaps in, but there they are anyway. And you're going to shine light onto that diffraction grating. So where does the light come from? Well, the light comes from a monochromatic. You know what mono means? Mono means one, and chrome means color. So you're talking about a light source with just one color, maybe pure red, maybe pure blue. So it's got one wavelength and one wavelength only. Like, you know what happens if you shine white light in? You'd end up getting rainbows at each order except for heading to 0. You're going to pass it through something called a collimator. So what does a collimator do? A collimator produces a parallel beam of light. So obviously from the monochromatic light source, the light is going to be spreading out in all kinds of different directions. You want a nice narrow beam of light. Let's say I've got pure red. So the pure red goes through my collimator, and I shine it through my collimator onto the diffraction grating as such. So there's my ray of light coming in. And that ray of light should hit the diffraction grating at right angles. So make sure that you adjust your turntable so that that diffraction grating is at right angles to the beam. Sometimes the light images you're going to form are too bright. So there is a little gap through which they pass through. That's called the aperture in the collimator. So if the rays of light, if the images coming through are too bright, you can actually reduce the size of the aperture, and that will cut down on the amount of light shining onto the diffraction grating. So they may ask you that. There's little adjustments that you need to make. You'll find this when you look at the experiment, what the adjustments are in order to get a better result overall. So anyway, my beam of light from my monochromatic light source passes through the collimator and hits my diffraction grating at right angles. What about the turntable? Well, you want the turntable to be level. So you have these leveling screws. Sometimes the images you get formed over here are a bit lopsided. The angles on one side might be greater than the angles on the other side. So one of the things you may have to do is level up your turntable. These leveling screws will allow me to do this. So, there's probably about 3 or 4 adjustments you need to know that they commonly ask. Anyway, what happens then? Well, what happens then is the light will diffract and the light will interfere. We did all this in previous lessons. And you end up getting bright images, bright and dark images. You'll get a bright image straight through. So a bright image will go straight through. We call that n equal to 0. You'll also get a bright image at a certain angle above that central image. And you'll get at exactly the same angle, because the bottom half, as you know, is symmetric. You'll get another bright image at the same angle below. They're the first order images. You'll also probably get second order images. That's a certain angle above the central normal. And you'll get another bright image at the same angle down here. Do you know what we call those images? We call the one right in the middle, we call that n equal to 0. And then you've got the first order image above and below. And the angles of these should be the same. So when you do the experiment, you might measure both of them and then take an average. Here's your second order image, n equals 2. Anyway, you want to know the angles at which those images are formed. So in order to do that, we have a telescope, and the telescope focuses on the images. You're able to rotate that telescope in that direction and in this direction. And on your turntable, you have a vernier scale, a scale that is calibrated to read degrees. You know, it's often a good idea to make sure that central order image, n is equal to 0, is at theta is equal to 0. That makes the experiment quite easy then to measure the angles. There's an angle above and below here. It's called the angle of n equal to 1 theta. And the angle of n equals 1 below should also be theta. But as I said, that mightn't be the case. They'll ask you certain reasons sometimes why thetas vary. And it may be that the turntable is not level. It may be that that incident beam is not at right angles to the diffraction grating. So there's a number of adjustments that you need to make that you'll read about in your experiment. So you'll average those two angles when you do the experiment once you've made all the adjustments. So what have I got? You've got to be able to draw that diagram. You've got to know the main parts, which are collimator, turntable with diffraction grating on it, telescope. This here is a vernier scale. I'll write that down. That will measure the angles for you. And then you know the formula that you're going to apply when you do your calculation. The formula is your diffraction grating formula that you've proved already. N lambda is equal to d sine theta. Okay, so that's a very, very short lesson. And the next thing you should do after doing that lesson is the experiment, which is L5, to measure the wavelength of light using a diffraction grating.